Hi, everyone. I want to start with a special announcement. Next class, that shouldn't say tomorrow, that should say Wednesday. Wednesday, we're going to go to lunch 2 that day, just that day. So come to class before you go to lunch on Wednesday. I put an announcement on Mount Notre Dame also, and I set up a email reminder to send out to you guys Wednesday morning. So I've done everything in my power to remind you that we're going to class first on Wednesday. Okay? Everybody's cool? If you feel like you're going to forget, make yourself an extra special note or reminder in your phone or something. Find your best friend to be like, hey, when you see me on Wednesday, put me in a headlock and drag me to class first. Don't let me go to lunch. Steal my lunch and take it to class so I have to come find you. You know, something. Okay. Again, that's a one-time thing, hopefully. So, good. Today, we'll start with questions. Does anybody have questions from the homeworks? I think we asked you guys, or we said you guys could do like 1 through, I don't know, like 22 or something. Sounds about right. Ariana. Sure. Let's take a look at what 16 said. That's not the right chapter. Grab that. Drop her in. Okay. So 16 says we're going to do BA minus 3 times CD. So the first thing I'm going to do is calculate BA. So again, we're doing head minus tail. The head is going to be the part that's under the arrow, and the tail is the part that's at the end of the arrow. So head minus tail is going to be 3 minus 5. Oops, right this way. And then tail is going to be 1 minus a negative 4. So I have negative 2, 5. And then CD, again, we're doing head minus tail, so I'm going to have negative 1 minus a negative 2. And then 6 minus 9. So that's going to be 1 comma negative 3. So now if we do BA minus 3 times CD, we have negative 2 minus 3, comma, 5 minus 3 times negative 3. So that's going to be negative 5, 20. Does that feel okay?
Yeah, pretty good.
No problem. Anybody else? Okie dokie. Today then, we're going to pick up where we had left off in section 8.2. Talking about vector operations. I think the next thing that we had to talk about was the dot product, right? Is that where we left off, I think? I teased it. I guess I could look. Blah, 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 blah. Yeah, dot product is what we teased coming next. Okay, so last time we talked about 3 vector operations: addition of 2 vectors, subtraction of 2 vectors, and the scalar product of a vector and a real number. Today, we're going to be talking about dot product. So the dot product occurs between 2 vectors. And the way we calculate a dot product is we do the first component of the first vector times the first component of the second vector. And then you add that to the product of the second component from the first vector times the second component from the second vector. What do you notice about the product here? If we're doing the dot product of two vectors, the result is a real number, not a vector. So vector dot product another vector is a real number. Now, keep in mind that this is kind of poopy, because if I have like 3 times 2, we mean multiplication. If I have 3 times vector v, we're talking about scalar multiplication. And if I have u dot v, we're now talking about dot product. So again, that dot has 3 different meanings. How do you tell which one we're talking about? Context, right? Number and number, we're talking multiplication. Number and vector, we're talking about scalar multiplication. Vector and vector, we're talking dot product. Right? So again, have to be careful and think about, okay, what is the context here? We actually are going to use dot product to do quite a bit of stuff. So let's look at some basic properties of dot products that we can use to make our lives perhaps a little bit simpler. So there's 5 basic properties for dot products. There's the commutative property, where u dot v is equal to v dot u. There's a multiplicative identity. If I take the 0 vector dot product with any vector, we get the number 0. Notice that this is a bold-faced 0, meaning it's a vector, the 0 vector. This is a regular-faced 0. That means it's the number 0. There's a distributive property where the dot product can distribute through addition or subtraction, either from the left or from the right. It doesn't matter. There's a scalar associative property that says if I have a scalar multiple of a dot product, I can multiply the scalar to the first vector and then do the dot product. I could multiply to the second vector and then do the dot product. Or I could do the dot product and then multiply the scalar through. All 3 of those are equivalent operations. And the last one is the magnitude property that says that a vector dot product with itself is equal to its magnitude squared. Remember, the vertical bars, when they're surrounding a vector, don't mean absolute value. They mean magnitude. I think in the homework I ask you to prove these things, but let's prove the first one here together, just give you kind of a feel for how do we go about doing this, okay? So I'm going to start by just defining 2 vectors, u and v. If you don't like u and v because you think the letters look too similar, you could use a and b. It doesn't matter. They're just names, right? So I'm going to start just by defining 2 vectors in component form. So vector u is u1, u2. Vector v is v1, v2. And what I want to do is I'm going to start with u dot v and try to end up with v dot u. So the first thing I'm going to do is just use the definition of a dot product. So that means I'm going to have u1 times v1 and then u2 times v2. Now remember, u1 times v1 are just multiplication of real numbers, right? And I know that multiplication of real numbers is commutative, so I could rewrite that as v1 times u1, and likewise rewrite the second product as v2 times u2. Everybody's good with that? No big deal. They're just real numbers. I can multiply them any order I want. If I then use the definition of the dot product again, we'll notice that the v's are in front now. So that dot product would have been v dot u. And hey, look at that. It's exactly what I wanted, right? Was u dot v equal to v dot u? Oh, we're done. This kind of pattern where we start with a dot product, use our definition to convert it into the sum and product of real numbers, use our properties of real numbers to kind of shuffle things around, and then our definition of dot product to put it back into a dot product is should be a familiar pattern for these. It's the same kind of idea we did a lot in geometry when you proved your congruence theorems. Usually you turned it into an equality statement, manipulated the equality statement, and then turned it back into a congruence, right? Should feel like a familiar pattern. Often a very good way to do this kind of a proof. Okay. Let's also do a numeric example just to kind of hammer this calculation home, since it's one that you'll kind of do a lot. So here we're given three vectors, u, v, and w. Now notice u and v are written in component form, but w is written in this other form. Does anybody remember the name for that other form w is written in, whereas 8i plus 4j? Remember what we called that? Be good if you did remember. You'd want to, but definitely by the time the test rolls around, you want to make sure you know the names. This would be called linear combination form, is what we called that. And given that all my definition for dot product was in component form, first thing I'm going to do is change that vector w from linear combination form to component form, so it's clear how I do the dot product. So the way I do that is just the coefficient on the I becomes the x component, and the coefficient on the j becomes the y component. Very easy to move back and forth between linear combination form and component form. Everybody's good there? Okay. So now if I wanted to do u dot v, well, I'm going to take the first component of u, multiply to the first component in v, and then add that to the first component from, or second component from u, multiply to the second component from v. So I get negative 17. Again, dot product of two vectors is a real number. So no vector, just a real number. So w dot v. Well, now that I've written w as a component form, this is really easy, right? First component of w times first component of v plus the second component of w times the second component from v. So it gives me negative 8 plus 20, or just 12. The next one, I have 5w dot u. Probably the way that I would do this, I'd go back and I note that, hey, the scalar associative property says that I can do that scalar multiplication any way I want. I would probably do it here, is the one that I would probably use. Just to keep all the numbers kind of as small as I can for as long as I can. So that'd be 5 times, and then I'll do the dot product of w and u. So 8 times 2 plus 4 times negative 3. So 5 times, 16 plus negative 12 is just 4, and 5 times 4 is 20. Now, could have you multiplied the 5 to the W first and then done the dot product? Sure! You'll get the same answer. That's just the way that I chose to do it because, again, at the end, all I had to do was 5 times 4. If I did 5 times W first, I'd have, 40 plus, or 40 and 20, and then I'm multiplying those to something. It just, numbers can get kind of big. I'd rather just, keep everything as small as I can for as long as I can. Makes the mental math easier for me. But if you're doing that on the calculator, who gives a poop, right? Calculator isn't bothered by it. All right, and then part D. So again, a couple of options here. Probably what I would do, now I notice there is a distributive property, but notice in doing the distributive property, one dot product turns into 2 dot products. I think I would rather just do the subtraction and do the scalar multiplication and then do the dot product. That feels like the easier order of operations to me, where I'm not going to forget to do something or goof something up or whatever. Everybody okay with that? Okay. So that's going to turn into U minus W is going to be 2 minus 8, negative 3 minus 4. Oops, that's going to be a dot. And then 2V is going to be 2 times negative 1, 2 times 5. So if I do that dot product, I'm going to have negative 6 times negative 2 plus negative 7 times 10. So that's going to be 12 minus 70, or negative 58. You guys feel okay doing this? Again, the calculation itself, pretty straightforward, right? Just multiplying a couple of things and adding them together. Not a big deal. So let's start looking at some applications here. One place that the dot product can come up is if we're interested in the angle between two vectors. So let's see what that's going to look like and how the dot product plays into that. So let's see. I'll have that little guy I'll call U. And this longer guy I'll call V. And what I'm going to be interested in then is this angle between the two vectors. Everybody okay there? What is this kind of starting to look like here as I draw this picture? Okay, a triangle, I would say, even more so, though. So let's complete the third side of this triangle, yeah? So I'm going to draw, for the third side of my triangle, I'm going to draw this vector. So remember how we add vectors, we add them head to tail. So I'd have U plus this vector in red is going to equal my vector V in green there. So what does that something have to be if I add that and I get v? Just subtract u from both sides, right? So this vector must be v minus u. Is everybody okay there? So now all I'm going to do is I'm going to use the law of cosines to say that the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. Or theta is just that angle between vectors u and v. Everybody feel okay with what I plugged in there? Just the law of cosines, right? All right. So what I'm going to do next is I'm going to evaluate these guys. How do I evaluate those? Well, the three that I highlighted. I'm going to use the magnitude property for vectors to rewrite those magnitudes squared as the product of the vector with itself. Oops. Okay. Now I need to deal with this. How am I going to do that dot product? Well, I have a distributive property for dot products, so basically I can just FOIL that out. Okay, well, great. I'm just going to write that. And it's not really where I thought that would pop up, but whatever. Now, if I subtract v dot v from both sides and u dot u from both sides, I get that. And I'll divide both sides by -2 times the magnitude of u times the magnitude of v. I have that. So the cosine theta is the dot product of u and v divided by the magnitude of u times the magnitude of v. Little surprising that the dot product would be related to that. Or if you wanted to, you could do the cosine inverse of both sides and write it as theta is the cosine inverse of u dot v divided by the magnitude of u times the magnitude of v. Everybody's okay with what we did there algebraically? Would I ask you to do that again? No. Do you need to use the formula? Yeah. That's what we did it the hard way once, so we have the easy formula to use from there on out, right? Thank you. All right. Keep in mind, since we're using cosine inverse, arc cosine, that the angles that it can output are only between 0 and 180. Is that a problem for us? No, why not? If you think back to geometry, we always describe the angle between two lines as the smaller of the two. So we never do it this way, right? So between two lines, are you ever going to get an angle that's bigger than 180 degrees? No. Because if it was bigger, you just go the opposite way, and then it's something between 0 and, you know what I mean? So it's like, okay, great. No problems at all. I love it when things just like work out for us. Let's do a numeric example just to make sure we have this all okay. So let's say we want to find the measure between the vector 7, negative 6 and the vector 2, 2. Now it's worth pointing out in this formula that you have two different multiplication dots going on here, right? The one at the top is dot product. The one in the denominator is just regular real number multiplication. So don't get confused on that. Oh, I'm going to sneeze again, I think. Oh, it's being stubborn. My eyes are watering. Does that ever happen to you guys? Ah! All right. So I need three things to plug into this formula. I need the dot product. So let's calculate that. So that's 2. I'm going to need the magnitude of u. How do I calculate the magnitude of a vector? Square root x squared plus y squared. So 49 plus 36 is 85. Am I going to worry about reducing any of these radicals that I'm creating here? No, because they're going into the cosine inverse anyways. Who cares what they look like, right? I sure as heck don't. It's all going in my calculator anyways. It's not a final answer. So I don't care if I can reduce the radical or not. I see the square root 8 for the magnitude of v, which I know I can reduce, but I don't care because it's just going in my calculator anyways. So cosine inverse, and then I'm going to use the fraction command. Very good idea to use the fraction command here because to get the division to work correctly, you're going to need a bunch of parentheses here that just I don't really want to have to think about. The beauty of that fraction command is I can just type it in my calculator exactly like it looks like on my sheet of paper, and the calculator will do exactly what I think it's going to do. So I get 85.6 degrees or thereabouts. Is everybody okay with what I did there? A real basic check you can do is you can just plot the two vectors and eyeball. Does that look like, enough? So I don't know, 7, -6 would be there. 2, 2 would be there. That look like 85.6 to you? As near as I can tell, seems perfectly reasonable. Now, is that kind of the check we just did? Is that like a perfect catch? No. But like, if you did something really wrong, you're going to catch it, and it just takes a second to do it. So if you feel like doing that, if you're looking to check, if you're like, ooh, that doesn't seem reasonable to me, you can always do that and check real quick, right? So you get an answer that you weren't like, oh, that's a weird looking answer. Draw the picture and just double check, right? If you forgot to do something like the cosine inverse, you'd catch it real quick. Or you did sine inverse instead of cosine inverse or something silly like that. It'll definitely catch those because they'll be way not close. Well, unless you're really close to like 45 or something. All right. So let's think back now for a moment to the unit circle. What was cosine? Well, let's think here. A special situation is when the angle between two vectors is 90 degrees. We call that orthogonal if the angle between two vectors is 90 degrees. So orthogonal is just like the vector term for perpendicular, right? But it basically means the same thing, right? So if we think back to our formula, we know if the angle between two vectors is theta, then cosine of theta should be the dot product of u and v over magnitude of u times the magnitude of v. So if if theta is 90 degrees, what is cosine of 90 again?
0.
Yeah, that's 0. And when is a fraction equal to 0? When the numerator is 0. Excellent. So in all reality, to check to see if two vectors are orthogonal, all we need to do is check to see if their dot product is 0. And in fact, that's going to be what we'll use as our definition for orthogonal. So we say that two vectors are orthogonal if and only if their dot product is 0. Notice that that definition is if and only if, so that means if two vectors are orthogonal, the dot product is 0, and also if the dot product is 0, then those vectors are orthogonal. Let's do a numeric example just to kind of check to make sure we got it. So it says to show the vector -5, 8 and 16, 10 are orthogonal. So WTS, want to show is that this dot product is equal to 0. Okay, well, easy enough to do that. The dot product would be -5 times 16 plus 8 times 10. That's -80 plus 80. So I do get 0. That's it. Oh, wow. It's like the easiest thing we'll do all day. Show two things are orthogonal. I just got to show that they When I do the dot product, I get 0. Oh. Huh. And dot product's a pretty easy calculation to do. We're just multiplying and adding whole numbers together, basically. I mean, they don't have to be whole numbers, but like, let's get real. They're probably going to be whole numbers. That's all right. That's all right. We're going to kind of continue into 8.3 and talk about some more applications of vectors. So the first application is one that you're already quite familiar with. So you remember when we did the navigation problems in first semester? These we can do instead now as a vector problem. Does it change materially how we did this? No, man, the procedure is going to be the same. We're just going to use different names for stuff, which I love. I love having real names for things rather than just like you do this and then you add some stuff. And it's like, let's give names for these things because now we can talk about as the x component or the y component or resolve the vector or blah, 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 blah. All right, so the boat leaves a port at an average of 40 knots, traveling for 2 hours on a course of 215 degrees. So I'm going to call this vector f for first. The magnitude of f is the length. So that's just going to be 2 times 40. So 80 nautical miles. And then we're told the direction of f is the course 215 degrees. But remember, a course is the same thing as a bearing, not a standard position angle. So I'm going to convert that into a standard position angle from a bearing. How do I draw a bearing? Starting from north. Yeah. So we start from due north and we go clockwise. So 90, 180, and then like 35 more. But what we really want is the standard position angles, which is 90, 90, and then 55 more. So 90 plus 90 plus 55 is 235. So I can resolve vector f into the standard or the component form vector by doing the magnitude of f times cosine of my standard position angle, comma the magnitude of f times sine of my standard position angle. Everybody's okay there? It says then the boat turns at a bearing of 162 degrees and travels 55 knots for 3 hours. I'm going to call this vector s for second. The length of vector x, s, its magnitude is going to be 3 times 55, or 165 nautical miles. And the bearing, we're told, is 162, but as we just discussed, a bearing is not the same as a standard position angle, but we can certainly find that standard position angle from it. So 162 degrees starting from due north is 90 and then 72 more. Meaning that little piece would have been 18. So my standard position angle, 90 plus 90 plus 90 plus 18, I guess we'll draw that as a green one, is going to be 288. So I can then resolve vector s to the standard position angle by doing the standard position vector, component form vector. It's the magnitude of s times cosine of 288. And then the magnitude of s sine 288. to find my resultant vector, I'm just going to add vector f plus s. And now it's going to be calculator time. To add two vectors, I just add them component-wise. So I'm going to do 80 times cosine of 235 plus 165 times cosine 288, which I get 5.10. And then I have to do the same thing with sines instead of cosines. That gives me negative 22246. So to get the magnitude of that vector, its length, we do that. So that's 22251. And to get the direction, we're going to plot that resultant vector. So I went 5 over and then negative 222 down. So something like that. So my standard position angle is going to be 360 minus phi. And we all calculate phi the same way. Tan inverse of the absolute value, my y component of r divided by my x component of r. So that's just calculator time. So tan inverse. And I'm going to pull the absolute value because I think I'm going to try to screen grab these values. And then we'll do the oops. So we'll just do 22222 divided by this guy. So I get, oops, I forgot to do 360 minus that. Oops-a-daisy. So 271.3-ish. So that's my standard position. If I want it as a bearing, then I have to do a little bit of extra whatever to it, but that's the gist of it. Jean-Paul. Certainly. What do you notice? Basically the same procedure as we did first semester. We just have some different names to things, right? Now instead of like doing this all with triangles, we're doing it all as vectors, but the process, the arithmetic, the steps, identical, right? Which is lovely, right? I love when it's like I'm doing the same thing but calling it a different name. Because then there's really, all I got to do is remember a new name. Whoop-de-doo-doo. Okay. The next example I have is one that's not as familiar, but let's say we want to, but before we get to that example, we want to talk about something else. So let's say we want to take a vector and break it into like the sum of two orthogonal vectors. Well, okay, Mr. Kulik. Like if your vector's 3, 4, I can do that. I mean, I'll just do, vector 3, 0 plus the vector 0, 4, right? Like big whoop. You act like that was going to be hard, like that was real easy. Okay. Sure. What if we make this a little bit harder? What if I want to break a vector into two orthogonal vectors, one of which is in the same direction as a third vector. So I give you a vector u, and I say, okay, break this vector u up into two orthogonal pieces. One of those pieces has to be in the same direction as a third vector. This we'll call vector v. So let's draw a little picture to kind of illustrate what's going on here. So here's gonna, well, let's draw it more like this. Here's gonna be my vector u. There's some vector v. And what I want to do is I want to create two vectors here that look like this. So the vector in green we're going to have a name for. We're going to call this the projection of vector u onto vector v. So the v is the subscript. What we're projecting it onto is the subscript, and the vector that we're projecting is the argument. So we're taking u, and like we're projecting u onto this other vector v. Okay. Well, fine, sure. I'm going to call this blue vector then w. And here's the beautiful part, is if we know how to calculate this projection, and we are given already our vector u, I can find w just by subtracting the projection from u onto v from both sides to get w, right? So what we're really just left with is how to calculate this. We're not going to do the derivation for that here today. Instead, I'm just going to give it to you as a formula, and we're just going to do it. So given two non-zero vectors, u and v, the projection of u onto v is the dot product of u and v divided by the magnitude of v squared times vector v. So I want you to note this quantity right here is a scalar. That's just a real number, right? So this is a scalar multiplication of vector v, which is exactly what we'd expect if it's going in the same direction as v, but possibly shorter or longer than v, right? Not a surprise there. Now keep in mind, to do this problem, do we really need the length of vector v specified? Not really, right? If all we need is our vector, our projection to be going in the same direction as v, all we really need is the direction. We can just specify v to be some length. What length do you suppose we'd use if we're not given a length for v? 1. 1. We're going to treat it as a unit vector if we're not given a length for v. So I'm going to drop in these 2 points, but this is exactly the 2 points that we just mentioned, that the magnitude of v doesn't really matter. We can just kind of, if we're not given a magnitude of v, we can just kind of assume that that magnitude is 1. And then for part 2, that basically just pointing out that this is a scalar multiplication of v is all we're really doing here. All right, let's do a numeric example here to just practice doing this calculation. So it says, find the projection of u onto v, then express u as the sum of 2 orthogonal vectors, one of which is the projection of v onto u. Okay. I meant the projection of u onto v, excuse me. So to do this vector projection, I need 2 things first. I need the dot product of u and v. So let's calculate that. And then I need, oops, that's supposed to be squared. And then I need the magnitude of v. Well, really the magnitude of v squared. Let's write it that way. Now keep in mind, when I square a magnitude, it's just going to blow up the square root on it, which is lovely. I love that because now it's like the arithmetic is just less of a hassle. 36 plus 16 is 52. I'm going to go ahead and reduce that. 14 over 26 is 7 over, or 14 over 52 is 7 over 26. And then I'm just going to do the scalar multiplication. So 7 over 26 times 6 is just going to be 21 over 13. I reduced as I multiplied. And then 7 over 26 times negative 4 is going to be negative 14 over 13. Again, I just reduced as I multiplied. So there's my value for, or my vector for the projection of u onto v. And then to get my vector w, I'm always going to do u minus the projection of u onto v. So 3, 1 minus 21 over 13, comma, negative 14 over 13. So to do that, I just need to make common denominators. So 3 is really 39 over 13. 21 minus, or 39 minus 21 is 18 over 13. 1 is really 13 over 13. So 13 minus a negative 14 is 27 over 13. So I can say that vector u then is my projection plus this vector w and a quick little check you can do. 21 plus 18 is 39, which divided by 13 is 3. Negative 14 plus 27 is 13, which divided by 13 is 1. So Feel pretty good about that. Okay. So this new operation of projections is going to come in handy. Oops, that's not what I want to press. To do the following kinds of story problems. How many of us are currently in a physics class or have taken a physics class? Handful of us. This kind of problem should sound quite familiar. Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? Physics students, this problem is kind of a hassle, right? Whenever we have a force being applied at an angle, right? It's kind of like you tilt the axes and you do some weird stuff and have to like make up some physics to avoid having to do trigonometry and like worrying about positives and negatives. Ugh. I'm going to do it all as a vector problem. This is actually quite an easy problem to do as a vector problem. Although we need to like prove a little stuff to show like why it's going to work this way every single time. But here we go. So I'm going to start by drawing a picture of my forces. So I have, my hill, right? So I'll call that my hill vector. And it says it's an angle of incline in the problem. So that means like this would be 25 degrees there. Everybody agree with that? And by the alternate interior angles theorem from geometry, that's a 25-degree angle there. So my standard position angle for that hill vector is 360 minus 25, or 335. My second force going on, or my second vector, is Kyle and the sled. Now, the only force acting on Kyle and the sled is gravity. Gravity is pulling straight down. So I know that the magnitude of gravity is 165. And if I want the angle then, that's just going to be 270. Everybody okay with this so far? All right. Notice what aren't we given any information about? The length of the hill. What am I going to do? Nope. I don't need to find it. I'm just going to assume that it's 1. Because what I'm going to be doing here in this problem to find the amount of force going down the hill is I'm going to project my force of gravity onto the hill vector and then calculate the magnitude of that projection. So if I want what is the amount of force going down the hill, that's going to be the projection of gravity onto the hill, and then we'll just take the magnitude of that. That's what we're looking for. So far, so good. Okay, so let's do that projection. Before I do that, though, I should resolve these vectors, right? Well, the hill vector is going to be 1 times cosine 335, 1 times sine 335, just magnitude times sine or cosine of the angle. And my gravity vector is going to be 165 times cosine of 270, which is 0. And then 165 times sine 270, which is -1. You could have also just gotten that from looking at the picture, right? It just straight down, gravity is going straight down on the y-axis, 165 units. It's going to be the point 0 -165, but either way. All right. So my projection here is going to be G dot H over the magnitude of H squared times H. Okay. Well, let's do that dot product here real quick. So that's going to be cosine 335 times 0. Well, that's okay. I guess I don't need to do that part. And I'll have sine 335 times -165. Oops. I said -165, not 65. So 6937. And again, the magnitude of H is just 1, so that's 1 squared. Then we have times H. So that's just some scalar multiplication. So, oops, 6973, not 37. Dyslexia. All right, I got this times cosine 335, and then this times sine 335. So we have 63, 20, -29.47. And then we just need the magnitude of that. And I get 6973. Wait a second. That number looked familiar. Didn't we see that number pop up earlier, 6973? Where did that happen already? Happened right there. It was just the dot product of G and H. Wait a second. Wait a second. Is the magnitude of the projection just going to be equal to the dot product? Is that true every time?
Yes.
No. But it's true under certain conditions, which we'll talk about next time. So I'm going to leave you on a cliffhanger here. Ha ha! Everybody's going to be so excited to tune back in next time. That's an enormously helpful time-saving result, though. So those of you that are in physics are like, ooh, yeah, just resolve these two things into vectors and do a dot product and be done. No tilting axes, no weird made-up physics stuff to get around having to use trigonometry. Like, I'm just doing a dot product. That's it. Under certain conditions, that will be it. Yes. At this point, you can through the end of 8.4, which we haven't finished yet, you can do up to 50. I'd probably stop when I get to these, like force diagram problems till I saw the rest of this, because we got another example or two, and then talk about like, when is this true? It's a very exciting result. Anyways, I'm going to stop here though, because it feels like it's a good place to stop, because it was as far as I got with fifth hour. And if I do more than one class than the other, I'm going to end up getting so unbelievably confused. So